Hello everyone, hope you guys are doing good. So before we discuss the hardcore kinematics and dynamics of robotic systems, we have to find out certain tools which are going to make this discussion easy. One such tool is homogeneous transformation. So let's start the discussion. In one of the earlier lectures on primary issues of robotic manipulators, we discussed a Twolink manipulator in detail. And in that, if you recall, we discussed how this point at the end effector is positioned and oriented corresponding to some base frame over here. So in that particular context, we identified two types of expressions, one corresponding to position of the end effector and the other corresponding to orientation. So for position, we said something like this, that we have a frame of reference to start with, which is the zeroth frame or frame 0, x0 and y0. And then at the next joint, we had another frame, which was x1 and y1. And we had another frame similarly over here, which was x2 and y2. So for the position expression, we identified x2 to be equal to a function of thetas. Now these thetas are defined over here like you have theta 1 at this particular place and you have theta 2 over here. Now on top of that, you identified that this length is a1 and this length is a2, and in that context this function was rewritten like this, that this is a1 cos of theta 1 plus a2 cos of theta 1 plus theta 2, both combined. Now similarly, you identified another expression corresponding to the y-coordinate, and that was also a function of thetas. So in order to differentiate the two, this can be f1 and this can be f2, and that was a1 sine of theta 1 plus a2 sine of theta 1 plus theta 2. Now this was fine, corresponding to finding out the position of this point with respect to the not moving frame, which is called frame 0 in this case. Now we were also interested in finding out how this frame is oriented, how this end effector is oriented corresponding to this not moving frame. And for that reason, we identified another matrix, and let me use a different color for that. And that matrix was corresponding to rotation of frame number 2 with respect to frame number 0, and that was defined like x2 dot x0 and y, sorry, this was x2 dot y0, and this is the first column. The second column was y2 dot x0, and this was y2 dot y0. And then we use the direction cosines to find out the expressions corresponding to theta 1 and theta 2, and that turned out to be, you have cos of theta 1 plus theta 2, and you had minus sine of theta 1 plus theta 2. This was sine of theta 1 plus theta 2, and this was cos of theta 1 plus theta 2. Now if you observe how we have defined this frame over here for the end effector, we have two disjointed representations, one which corresponds to position and the other which corresponds to orientation. So in that particular context, I wish to find out one particular formulation which combines the two, and that would be what we call homogeneous transformation. So combining the position and orientation together, you are going to find homogeneous transformation to be a matrix. This matrix is going to be a 4 by 4 matrix. And in that, you are going to find one space reserved for orientation. This space is generally 3 by 3 sized, and then another column which is going to be 3 by 1 column reserved for translation. So this is going to be D, this is going to be rotation. And then you're going to find out the last row to be generally 0, 0, 0, and this element is going to be 1. Now the way it is structured, you can obviously see that this is a specific structure which is going to potentially help us out in terms of finding out subsequently the forward kinematics and understanding the inverse kinematics and all the subsequent analytical approaches. So in that particular scenario, you can readily identify that we are going to combine the two representations that were previously separated in a single formulation. But having a compact representation is not the only benefit of using homogeneous transformations. Obviously, these are represented like matrices. So potentially we are going to make use of linear algebra to handle multiple matrices together. So that is going to be potentially another possibility. And then since these are matrices, these are going to have specific properties. And these properties can be manipulated. For example, you can have the rotation matrix, which is going to belong to a special orthogonal class. So that is potentially going to be helpful in finding out for multi-body systems how the orientation is going to be associated with the end effectors. And on top of that, you must also realize that you are going to have multi-body systems. Now, which means that, for example, over here, if you have a robot, which is going to have multiple links connected together, eventually reaching to the final end effector, you would love to start from any starting frame over here, for example, and reach to the final frame over here for that matter. But in that particular case, you have to go frame by frame or link by link or joint by joint in order to move in the forward direction, eventually reaching to that final tool center point. Now, in that particular case, it would be very useful if we can associate these homogeneous transformations for all these frames. For this frame, for this frame, this, and all the way to the final tool center point. And if we can define these homogeneous transformations using the properties of the matrices involved, potentially we may find the computation of multi-body kinematics and dynamics to be much more easily manageable. So for that matter, we have to identify that kinematics, in this context, kinematics and dynamics is going to be potentially easier. So these are the major reasons that we use the homogeneous transformations. Now the big question would be from where we're going to start the discussion. So as we have mentioned earlier that homogeneous transformations are going to have two components. One corresponding to position representation and the other corresponding to rotation representation. So we are going to discuss position first and and then we are going to discuss the rotations and all the different possibilities and manifestation of rotation, and then we're going to combine them together. So this is how we're going to structure it. So let's discuss position representation first. Now, in order to understand the concept of position representation, we must start from a point P. Now, this point P is available in front of you, but it is not being localized corresponding to certain frame of reference. So we need to add that. Let it be like one frame of reference in front of you, like x0 and y0, the two axes, mutually orthogonal, obviously. So I can identify, because I'm using the subscript 0 over here, I can say that this is frame 0. So the origin of this frame can also be indicated like O0. Now in this particular scenario, if I use some appropriate scale, I can identify where the point P is located corresponding to the 0th frame, and that would be indicated like P0 to be equal to this vector. A vector where the first position is going to correspond to x coordinate, and the second location is going to be with respect to the y coordinate. Now, in that particular sense, I can, using that appropriate scale, I can start counting how many units I'll go along x direction. So let it be like 1, 2, 3, 4, and I'm assuming that this is going to be 5 units along x direction that I'll have the x coordinate indicated. So this is going to be 5 for that matter. And similarly, I can go certain units along y direction, the other axis, and I can locate the point P. And that would be using the same scale: 1, 2, 3, 4, 5, and possibly these are 6 units along y direction. So this point P is when associated with 0th frame, or located with respect to 0th frame, it is going to have a vector 5, 6 representing it. Now remember, P is not equal to P0. Here P is point itself, P0 is the representation of the point P in 0th frame. So similarly, I can have a vector representing or indicating the position of the point P, and that would be something like this. And this vector v1 is going to have the same coordinates as well. Now this is only one frame, but I can have another frame of reference defined, and the same point P can be represented with respect to that, and that would look something like this. Now you have another frame where you have subscript 1 indicating that it can be called frame 1, and you have x-axis over here, y-axis for that frame indicated as well. So O1 is the origin of frame number 1, and you have a vector v2 indicating the same point, or identifying the same point P with respect to now frame 1. And I can write that as well over here. Let me use a different color. So P1 is location of the same point P in the first frame to be equal to now a vector once again, but now this vector is corresponding to x1 and y1 directions. So that would be, in that sense, I can identify that it goes 1, 2, and 3 units possibly along minus direction, minus x1 direction. So this would be minus 3 as the first element, and it goes certain units along y direction. So this is possibly 1, 2, 3, and 4 units along y1 direction. So the same point P is, when represented in the 0th frame, is going to have the coordinates 5 and 6, and the same point P when represented in the first frame is going to have different coordinates corresponding to it. Whether you define it in this form or in a vectorial form, this is going to be the same result. And then I can say that in addition to that, we can have the particular frames correlated with each other as well. For example, if I say that how frame number 1 is oriented with respect to 0th frame, so this would be how frame with origin O1, X1, Y1 is positioned with respect to 0th frame. Now, in that particular scenario, you can see that O1 is placed over here and frame 0 is originated over here. So in this particular case, I can see that how I'm going to correlate the two. So in that particular scenario, with respect to frame 0, if I go, let me indicate that, along x0 direction, 1, 2, 3, 4, 5, 6, 7, 8, 9, and possibly 10 units along x0 direction. And if I go 1, 2, 3, 4, and possibly 5 units along y0 direction, so that would be how origin of frame 1 is oriented with respect to 0th frame. And similarly, I can write down O0 with respect to first frame. That would be equal to, using x1 and y1 as the guiding directions, this is going to be -10 and 5. So with this realization, now you can identify that position of certain points on such kind of representation is going to be corresponding to certain frame of references, and that is why we are going to make use of this kind of vectorial representation while discussing the homogeneous transformations. Now, rotation representation is the second part of homogeneous transformation. And in that, initially we must discuss a simpler case, that is of 2D rotation. Now in this particular scenario, you can identify that you have frame 0 indicated, x0, y0 are the axes corresponding to it, and then you have a rotated frame 1 with x1 and y1 as the axes. Now this rotated frame has been rotated by a value theta. Now with this realization that we need to find out how the rotation matrix is structured, I must make you recall that we identified that like R1 with respect to 0 arrangement, and that was because it is a 2D case, it is going to be a 2 by 2 matrix. And in that, the very first column over here is going to be how x1, the x-axis of frame 1 is how x1 is oriented with respect to frame 0. So this first column is going to correspond to that. And how that can be written down, this is going to be x1 dot produced with x0 and x1 dot produced with y0. Now this column is going to indicate that how x1 is oriented with respect to frame 0. Now similarly, I can write down the second column, which is going to be indicating how y1 axis is oriented with respect to frame 0. So this is going to be y1 dot x0 and y1 dot y0. Now, since you have this like a generic arrangement using the concept of dot product, you can make use of direction cosines and you can rewrite this whole matrix R10 using the angular displacement theta. And that would be when you take the dot product between x1 and x0, this is going to be how x1 vector is projected onto x0 axis, and that obviously is cos of theta because these are unit vectors. So I'm going to write down cos of theta over here. Similarly, x1, how this is oriented with respect to x1 is oriented with respect to y0 axis, that obviously is sine of theta, so I can write down that. Now coming back to the second column, y1 dot produced with x0, so y1 is this, x0, this is y0 and this is y1. So how y1 is oriented, that would require the angular displacement to be indicated. So this is also going to be theta. So with this realization that I need to identify how y1 is oriented with respect to x0 as the first element over here, so you can obviously see that it must go in the negative direction. So that's why it is going to be minus sine of theta. And then you have the other last element y1, which is this, projected onto y0. Obviously this is going to be cos of theta. Now this is how you have defined the rotation matrix, and in that particular scenario you can now recall that this is going to be the underlying rotation matrix that we are going to try to use. Although it is in a 2D case, we will see a 3D case subsequently, but at this particular stage you can readily identify the structure of these rotation matrices. What about I'm interested in not R10 but R01? What about that? What does that mean? It means that I'm interested in how frame 0 is oriented with respect to first frame. So this is kind of inverse of R10. So in terms of how we are going to structure it, this is going to remain still following the same procedure that we have defined earlier. In that case, now you have x0 axis dot produced with x1 and x0 axis dot produced with y1. So this first column is going to define how x0 axis is oriented with respect to frame 1 now. And similarly, you can write down y1 dot y0 dot x1 over here and y0 dot y1 over here. Now, since you know that the scalar product or dot product is commutative, that's why I can rewrite this matrix to be like this, that you have now x1 dot x0 and over here y1 dot x0, and over here you have x1 dot y0, and this is going to be y1 dot y0. And what we have done, just for the sake of clarity, we have reversed the order. x1 is brought on this side of the dot product and x0 is brought to the other. So that's why all these elements are rewritten, because we have realized that the scalar product is commutative in nature. So with this realization that you have got now this matrix, you can compare it with the R10. So compare it with R10. And if you observe very clearly, this is actually the transpose of R10. So we observe that it is equal to R10 transposed. Why so? I can make you see that. So the first row is x1 dot x0 and x1 dot y0, which is actually the first column of this matrix shown in green, x1 dot x0 and x1 dot y0. And similarly, the second row, y1 dot x0 and y1 dot y0 is the second column of this matrix, y1 dot x0, and this is also the same, y1 dot y0. So in that particular case, you can observe that this is actually equal to the transpose of it. And that is because you have taken the inverse situation. So this is R10 inverted. So in that case, I can rewrite the expression over here that R01 is actually equal to R10 inverted. But this inversion is actually very simple, that it is R10 transposed. And that was possibly, we still have to see the other properties as well, possibly a property of orthogonal matrices. So we will further see whether it is orthogonal matrix or not, but this property is seemingly becoming more interesting for us. We can now consider the 3D case. In this case, to start with, we have the 0th frame. And now you can see the three axes, x0, y0, and z0 axis. You can now say that you have another axis which is rotated about z0, and that would look something like this. Now you have, in this case, the rotated frame x1, y1, and z1. So in this particular scenario, you can obviously see that the frame has been rotated, frame 1 has been rotated about z0 axis. So in this particular case, I can write down the rotation matrix once again. Rotation of the first frame with respect to 0th frame is going to be a matrix, obviously. But since it is a 3D case, I'm going to have this size to be a 3 by 3 size. Now in this case, the very first column is going to be indicating how x1 is oriented with respect to frame 0. Similarly, the second column is going to indicate how y1 is oriented with respect to frame 0. And the third column is going to indicate now corresponding to z1 axis with respect to frame 0. Now in this particular realization, I can say that the first column is going to be, for that matter, x1 dot all the other axes of 0th frame, which is x0, y0, x1 dot z0. So this is going to be the generic structure of the x-axis of frame number 1 rotated with respect to frame 0. Now similarly, you can write down the second column, which is going to be y1 dot x0 and y1 dot y0 and y1 dot z0. Similarly, the third column, z1 dot x0, z1 dot y0 and z1 dot z0. So in this case, you have now a generic rotation matrix which is going to indicate any rotation. Now since in our case you have a special scenario, that the rotation is happening about z-axis by a value theta. So this is indicated by having the coinciding z1 axis, and this is the theta angular rotation which has happened. So I'm interested in finding out how this generic matrix can be transformed to fit well with the special case. Now in that particular scenario, I can readily see the pictorial representation, and I can write down that matrix now over here. So this would mean that if the rotation is happening about z-axis by value theta, so this would mean that the rotation of first frame with respect to 0th frame is going to be equal to rz theta, which is going to be equal to, now I'm going to plug in the values corresponding to the element, the dot products over here. So the very first thing is x1 dot x naught. So this is indicating that how x1 axis is rotated with respect to x naught. So that projection on the x naught axis of this unit vector x1 is obviously cos of theta. So I can write that one down over here. So this is going to be cos of theta. Similarly, you can see that you have the other element x1 dot y naught, which means that how this x1 is oriented along the y naught axis, so that is obviously sine of theta. So you can write that one down over here, sine. Let me displace it a little bit, sine of theta. And then the last one, which says that x1 dot z naught. So this is the x1 and this is the z naught, and obviously you can see that you have the 90 degrees between the two. So this is the 90 degrees angle. So dot product between two vectors which are 90 degrees apart is obviously going to be equal to 0. So that's why I'm going to write down 0 over here. Let's consider the second column. y1 dot x naught is the first term. So y1 is this in this direction, and x naught is obviously, you can see that happening over here. So that is going to be in the negative direction of the x naught by value sine of theta. So that's why I'm going to write minus sine of theta over here. Similarly, y1 dot y naught, and this is how y1 is positioned corresponding to y naught, and that obviously is cos of theta. So I'm going to write that one down, cos of theta. The last term is y1 dot z naught. So y1 is heading this way and z naught is upwards, and that's also kind of 90 degrees between the two unit vectors. So that's why it is going to be equal to 0. Now for the last column, I can once again see z1 dot x naught. So z1 is upwards and x naught is this way, which is obviously 90 degrees apart. So that's also going to be 0. Moving on, z1, which is this direction, dot produced with y naught, which is heading this way. This is also 90 degrees apart. So that's why that dot product is also going to be equal to 0. And then the last term is z1 dot z naught. So z1 is heading upwards and z naught is also coinciding with that. So vectors which are parallel and coinciding, obviously the dot product is going to be equal to 1. So I'm going to write that one down over here. So in this particular fashion, you can see that now you have got one special case indicated where rotation is happening about z-axis by a value theta, and that is going to be the rotation matrix that we have just formulated. Now similarly, you can find out the rotation matrices in a similar fashion about x-axis and about y-axis, and that I'm going to indicate in the next slide. Now here are some basic rotation transformations. The very first one corresponds to rotation about z-axis, the second one corresponds to rotation about x-axis, and the third one corresponds to rotation about y-axis. The z-axis rotation has been just derived, so you can memorize that. But in order to make some sort of reference point to memorize the other rotations, basic rotations, you can see that for X, it is the first row, first column element, which is 1. The others are in that row and column zeros. And similarly for the Y, you can have the second row, second column element to be 1. The rest are going to take their shapes accordingly. And for the Z, obviously, you have already realized that it is the third row, third column element, which is 1. Others are going to have their corresponding positions taken. So this is going to be just like a little trick to memorize the basic transformations. Now, more than that, I'm interested in finding out the properties of these rotations. So I'm going to make you recall that we have identified this property, that rotation taken inverse of came out to be rotation transposed. So over there we raised this suspicion that possibly this is because the rotation is going to be orthogonal matrix, is going to belong to the orthogonal matrix, and it is 3 by 3, so that's why it is 3 over there. Now this is one of the properties, but we need to see the other properties as well. Let's try to find out the determinant of rotation matrices. Take any of the matrices over here. Let's say I take rotation about x-axis, for example. So this is going to be 1 into cos of theta multiplied with cos of theta, cos square of theta, minus minus plus sine square of theta. So you can see that cos square of theta and sine square of theta added together is going to produce 1. So that's why, since other elements are zeros, so that's why this determinant turns out to be equal to 1. Similarly for this, you can counter check that. And similarly for this, you can readily identify that this is also going to be following the same route. So determinant turns out to be, in these cases, equal to 1. And that is one of the properties of the orthogonal matrices. And to be specific, it is, if it is always positive 1, it is going to be the property of special orthogonal matrices, not the general orthogonal matrices. Now on top of that, I can check whether the magnitude of columns or rows turns out to be equal to 1 or not. So let it be like written down over here, magnitude of rows, and for that matter columns, is what? Let it be like, if I consider this column, cos square of theta plus sine square of theta plus 0 squared is going to be equal to 1 because of the trigonometric property. Similarly over here, sine minus sine square of theta is going to cancel the minus sign over there, plus cos square of theta plus 0. So magnitude turns out to be for this column equal to 1. So 0, 0 and 1 squared under root turns out to be 1. So this is going to be, obviously, all the columns are having magnitude equal to 1. Similarly, you can check the rows as well. Similarly, you can check the other matrices as well. So rotation matrix, in this particular sense, we have checked that the magnitude turns out to be equal to 1. Now on top of that, I can check whether the axes are mutually orthogonal or not, or in that case the columns, or for that matter rows, are mutually orthogonal or not. So you can see and you recall actually in the previous derivation corresponding to this matrix, we started with this rotation matrix, and I'm going to rewrite that once again. That rotation was, if I make it quickly, it was x1 dot x naught, x1 dot y naught, and x1 dot z naught. And similarly over here, this was y1 dot x naught and y1 dot y naught, and this was y1 dot z naught. Similarly for this column, you had z1 dot x naught, z1 dot y naught, and this was z1 dot z naught. So you can see that this is x-axis, this is y-axis, this is z1 axis rotated, all rotated with respect to 0th frame. So this column, the first one, is orthogonal to the second column because these are Cartesian frames. The second one is orthogonal to the third one. So that's why this property over here is by design and by the virtue of these being the Cartesian frames, this is already fulfilled. So I'm going to tick that as well. So this is when taken care of, and this is when taken care of, and this determinant turns out to be equal to +1, and rotation inverse turns out to be equal to transpose of a rotation. This ensures that the rotation matrix over here belongs to a special orthogonal group of matrices which are going to have 3 by 3 sized. So, or in other words, rotation matrices are orthogonal matrices. And when these are orthogonal matrices, we are going to definitely get benefit from these properties. And this is what you're going to observe subsequently as well. For example, just for the sake of discussion, I can simply make you see that when you wish to take the inverse of a matrix, a 3 by 3 matrix, it turns out to be a bit difficult task because you have to take the adjoint of this matrix and then divide with the determinant. So if you have to go through that difficult lengthy route to take the inverse of it, rather than that, if you just change the rows with columns, or in other words, take the transpose of it, that would be much easier to handle analytically as well as computationally. So for that matter, I can readily identify that these properties of special orthogonality are going to help us out in greatly reducing the complexity of the computations. So that's why we are going to opt for rotation representation the way we have structured it over here. Now the question is that how are we going to use this concept? Consider a rigid body on which you have a point P already known with respect to the body attached frame, which is indicated over here, x1, y1, and z1. So this location is known with respect to frame number 1. And you're interested in finding out this location with respect to not moving frame or a frame which is not attached to the body. Just like the frame 0 indicated over there with x0, y0, and z0 axes. So when body S rotates, this frame x0, y0, and z0 does not move. Whereas the frame 1, which is x1, y1, and z1 frame, is going to rotate along with the rotating body. So I'm interested in finding out location of this point P with respect to 0th frame, given you know location of point P in frame number 1, which is body attached frame. So in that case, obviously you can use the concept of rotation because in this particular scenario, only rotation is happening. So when rotation only scenario is there, in that case, P naught or location of point P in the 0th frame is going to be equal to rotation of frame number 1 with respect to 0th frame multiplied with location of point P in the body attached frame, which is frame number 1. So this is going to be the formulation that we are going to use subsequently as well, with a little bit of modification that we are going to add the translation aspect later on as well. But at this particular stage, from a practical standpoint, this is how we're going to use the concept of rotation over here, multiplied with a vector P1, which is going to be known already. So this is going to be a vector, and this is the matrix that we have already computed. Now I can readily identify that homogeneous transformation is going to account for position and rotation together in a single matrix. and that is going to be homogeneous transformation of a particular frame, let it be ith frame, with respect to the previous frame I minus 1 to be having a 4 by 4 structure in which you have this kind of internal substructure where you have rotation of the ith frame with respect to I minus first frame and translation of the ith frame with respect to I minus first frame, and then you have a vector of 3 zeros and 1 over there. So this is going to be the structure, general structure that we will follow in subsequent discussions. Although there are certain variants in the homogeneous transformations generally, but since we are using them in our robotic manipulators, so this is the structure that we will follow. But obviously you can see that in this case the rotation representation, although we have explored the 2D case and 3D case both together, but in case of 3D case, if I make you recall that the rotation was having 3 columns. The first one corresponds to the x-axis and the rotation of that. Similarly, this corresponds to the y-axis, this corresponds to the z-axis. And on top of that, the properties were very interesting. The properties of rotation matrix were identified to be part of special orthogonal matrices of having 3 by 3 size. And this is a very big revelation. We will try to make use of these properties, and these properties being that the inverse of rotation is actually the transpose of rotation, which is actually going to greatly help us out in analytically solving the forward and inverse kinematics. We have identified that the determinant of rotation turns out to be positive 1, and we have also identified certain properties corresponding to the columns and rows being having magnitude to be equal to 1 and so on and so forth. So there are certain properties which are going to be greatly helping us out in further subsequent discussions. And similarly for the position as well, we have accounted for the 2D case and 3D case as well. And in that case, the vectors were identified like having x and y elements, and over here you have x, y, and z elements in that. But eventually, when we combine the two, we identified that the position of a particular point in a specific frame or in a not moving frame was identified to be, when having the rotation only, rotation of the first frame with respect to 0th frame multiplied with the position of the same point in the body attached frame. So this equation, which is going to be further augmented later on by adding the translational part in it, d10, is going to be greatly helping us out in the subsequent discussions as well. So we can now see that the homogeneous transformations, because of the way it is structured and because of the way they combine both position and rotation together, and the way the properties are structured, especially corresponding to rotations, those being part of special orthogonal group, are going to be very useful in the subsequent discussions in kinematics as well as in dynamics. But up to this point, we have only given the basics of homogeneous transformations. We still have to see that if you have a multi-body system where you have the robot having multiple joints and links connected together, eventually reaching to the point where you are actually performing the job. In that particular set of scenarios, how are you going to combine the homogeneous transformations corresponding to all these joints over there? So what is going to be transformations for this frame over here, this over here, and I'm randomly attaching these frames, but we will obviously have a specific scheme corresponding to that. So all these transformations are going to have their role to play in computing the forward kinematics going all the way to the tool center point. So in that particular set of scenarios, we are going to be interested in finding out all those homogeneous transformations, how these can be composed together and all that, uh, and how we're going to try to solve them as well. So this is going to be the discussion in the subsequent part of this series. We will see that later on. So this is end of part 1. And next time we are going to discuss composition and parameterization of rotations. So until that time, bye bye.